Welcome, this is CCNP Switch. I'm doing Chapter 2, Networking Design Fundamentals, and this is going to be in the Switch Foundation text. Our main thing here is talking about the campus network structure, the typical Cisco switches, and then comparing Layer 2, Layer 3 type switches, including multi-layer type switches. So let's first talk about our campus network structure. Our general hierarchy is going to be a three-tiered system: access, distribution, core. And we compare that against a flat network. With this structure, we can grow. It's flexible. With a flat diagram or with a flat network, growing is an issue. Security is an issue. Scalability is an issue. That's why the hierarchy model has become the premier structure for switched environments. So how we do this is, at the core layer, we do all high-speed switching. At the distribution layer, this is where we're going to do our policy-based connectivity, also our access control lists. Lastly is our access layer, and that's going to be our local and remote work groups and general access. So how is our network hierarchy, how does that support the needs of our small and medium businesses? It will help explain the benefits of that structured model. Here, with a small to medium-sized business, we could do a dedicated access layer, and that helps troubleshooting long-term and allow for growth. Some of our benefits is the scalability, redundancy, performance, security, manageability, and lastly, maintainability. It can grow as the organization needs it to grow. So some of the key principles for our hierarchy design is, again, there's three layers. Our distribution is going to be controlling our access control lists and our policy-based switching. These will be end devices, and our core will be our high-speed network. So the concept of a converged network, that's the combining of all resources like video, voice, and data onto one network. No longer having separate networks for specific devices. Converged. That means taking, regardless of the size, medium, small, large, putting it all on one network. So some considerations in selecting our appropriate switches for our network. We can have things like fixed ports that are semi-dense. We could have more dense ports, again, at a fixed port level. What happens when those don't fit the needs? We can have something more powerful, a more modular switch, like a Cisco 6500 or an 8500. That's going to be a larger chassis with the ability to grow as requirements grow. This is going to be more of a larger medium or a large business. So some additional considerations is, what about PoE or maybe wireless? If this switch requires that it's going to pass power, it may be PoE. Are there different types of switches? So far we've talked about fixed and modular. What about stackable switches? If we need a happy medium between fixed and modular, we have stackable. Stackable just allows us to combine multiple switches with dedicated wires, so they're a little bit more flexible. Not as flexible as a modular switch, but not as limited as a fixed port switch. Here we have the different layers. Our access, that's going to be our port security, our VLANs, our PoE, basic quality of service. Our distribution is going to be more high forwarding rates, maybe 10 gig, maybe redundant components, better security, better policy, link aggregation, and again, QoS. Our core layer, this is going to be our layer 2 and layer 3 support. Faster or the fastest forwarding rates, gig, 10 gig, redundancy, better link aggregation, and again, QoS. QoS is going to be standard throughout. So let's look at this one more time. Our access layer, that's going to be where we connect. Our distributions are going to take all of our access links and move them to a distribution layer. Our distribution layer will then connect to some core. That core is going to be a high-speed connection. That core will be the most expensive switches, and they may connect to multiple distribution points. For example, we may have multiple buildings, and we have our core network. So we have every building separated in their own little spheres. This building, access distribution, and then the distribution switches connect to the campus backbone. Also attached to that backbone is our data center. But everything focuses around our core network. So what are some devices that may operate at individual layers? So for an access switch, it could be something like a Cisco 2960 or even a 3850. Kind of depends on the level of the organization. Normally, the cheaper switches or the cheapest switches will be at the access. The medium price switches at the distribution. Because here we have a 3850, and on a larger business, that was their access switches. So it just kind of depends price-wise. And we're going to end at the very top with a core with a 6800 series switch, because these are going to be the most expensive. So again, hierarchy design, core, distribution, access. Why is it that design modular or module? Because we need to focus on performance, scalability, maintainability, manageability. When we have this type of structure, we can monitor the network and monitor performance. The hierarchy design addresses scalability issues, performance issues, maintainability, manageability, redundancy, security at the appropriate levels. That's the importance of this. We could do a collapsed core where there is no centralized core. Each distribution switch connects to all other distribution switches. Do you see how many links there are going everywhere? That just gets crazy to manage. If we centralize, it makes it more manageable. So let's go ahead and move into our layer 2 and multi-layer switches. So, combines functionality of a switch and a router. That's going to be a multi-layer switch. Offload software-based routing processes, packet rewrites to specialized ASIC hardware. Provides wire speed Ethernet routing and switch services. Optimized for campus LANs. And performance. The three major performance areas: packet switching, route processing, intelligent network services. So let's talk about a frame rewrite. The incoming frame checksum is verified to ensure that no frame is corrupt or altered during transit. The incoming IP header checksum is verified to ensure no corruption, no alteration. Our Unicast packet rewrite on output interfaces, the source MAC address changes from the sender's MAC address to the outgoing MAC address. Here, the MAC address is going to change depending on next device. We also have a time to live, which will be decremented by 1, so that the IP header checksum could be recalculated, and so that we do not have endless loops. The switch obtains the information needed for the frame rewrite process from the internal table, such as our CAM and TCAM tables. Some of these tables are cached in an ASIC or RAM. Multilayer switches build routing, bridging, QoS, as well as ACL tables for centralized and or distributed switching. Switch perform lookups on these tables to make better decisions. Multilayer switches deploy these memory tables using specialized memory architectures, normally CAMs and ternary CAMs or TCAMs. So a CAM table matches on two values, binary, true and false. They're useful for building tables that will search for exact matches. For example, my MAC address sends out what port? That could be a lookup. The primary table is used to make layer 2 forwarding decisions, but it's built by recording the source MAC addresses on inbound ports for all incoming frames so that we can map out the network. TCAM. TCAM matches it based off of three values, 0, 1, or X, where X is either number. TCAM is most useful for building tables for searching on the longest matches, such as IP route tables organized by IP prefixes. So again, slightly different from a MAC CAM table, but it's still some form of lookup table. The memory structure is broken into a series of patterns and associated masks. It stores ACL, QoS, and other information generally associated with layer 3 processes. In addition, Catalyst switches architecture support capability to perform multiple lookups in multiple distinct CAMs and TCAMs regions in parallel. As a result of the capacity to perform these multiple lookups simultaneously, Catalyst switches do not suffer any performance degradation by enabling additional hardware switch features such as QoS and IP-ACLs. In specific high-end switch platforms, the TCAM is a portion of memory designed for rapid hardware-based table lookups for layer 3 and layer 4 information. In the TCAM, a single lookup provided all layer 2 and layer 3 devices, forwarding information for frames including CAMs and ACL information. In a layer 2 table, all bits of information are significant for frame forwarding. For example, VLAN, destination MAC addresses, and destination protocol types. However, in a more complicated table associated with upper layer forwarding criteria, a full analysis may not be required. Some bits of information might be too insensual to analyze. For example, an ACL might require a match on the first 24 bits of an IP address, but not a concern with the last 8 bits. All fun stuff for our TCAMs. TCAMs also are used for looking up Cisco Express forwarding prefixes to make a routing decision. So our TCAM match region types are 3 types: exact match region, longest match region, or first match region. These are going to be different depending on their criteria. Exact match region, layer 3 entities for an IP adjacency. IP adjacencies are next hop information, such as a MAC address. That's not a layer 3 entry, keep that in mind, associated with an IP address. Other examples of exact match regions are layer 2 switch tables and UDP flooding tables, as compared to a longest match region, which is a multiple buckets or groups of layer 3 addresses entries organized in decreasing order by mask length. Last, a first match region stops looking after the first match of the entry. For example, a first match region is used by ACL entries. It's more line-based. CAM or TCAM protocol regions are region names, IP adjacency, prefixes, multicast, layer 2 switching, UDP flooding, and access lists. Here we have the iOS regional names, the lookup types, the key size, sample results. All this lovely, hard, in-depth information that will probably never be used. All good stuff though. Distributed hardware forwarding. The main function of the control layer between the routing protocol and the firmware data path include managing the internal data and control circuits for the packet forwarding and control functions, extracting other routing and packet forwarding related control information from Layer 2 and Layer 3 bridging and routing protocols. And that includes configuration data and then conveying the information to the interface modules for control or data path selection. Collecting the data path information such as traffic statistics from the interface module on the route processor. Lastly, handling certain data packets sent from the Ethernet interface module to a route processor. Layer 3 switching software employs a distributed architecture in which the control plane and the data plane are relatively independent, i.e., they work independently. The control path code, such as the routing protocol, runs on the route processor. Each interface module includes a microcode processor that handles all packet forwarding, the Ethernet interface module, and the switching fabric forwards most of the data packets. Our control plane focuses on the routing protocol and ARP routing table. Our data plane deals with incoming packets, our routing protocols, and outgoing packets. Right, so let's go and move on to our switching methodology. We've already covered this. This is all normal CCNA level switching technology. But process switching versus fast switching versus our Cisco Express forwarding, our CEF. The default switching mode now is CEF. It's less CPU intensive than fast switching or process switching. And a router with CEF enabled uses information from the tables built by the CPU as a better routing table. It uses this information both from the routing table and ARP table to build a hardware-based table known as the FIB, Forwarding Information Base, as well as the Adjacency Tables. These tables are then used to make hardware-based forwarding decisions. So part of our Cisco forwarding decision methodology also includes route caching and topology-based switching. Information from the routing table is used to populate routing cache. Regardless of the traffic flow, the populated route cache is called the FIB. The Cisco Express forwarding is the facility that builds the FIB. Here's what we talked about router caching. The first packet in a stream is switched in software by a router processor. Information is stored in cache tables as a flow, and then also switchable packages are switched in hardware. Topology-based switching, faster than route caching, even first packet forwarding by hardware. CEF populates the FIB with information from a routing table. CEF Processing, CEF Switch Location, that includes things like the decentralized switching, which carries out forwarding decisions on specialized ASIC interfaces or ASIC algorithms. Next is our distributed switches, our DCEF interfaces or line modules on a layer 3 switch handled forwarding decisions independently. These are just distributed switches at layer 3. Here we talk about our CEF processing. And remember, CEF uses specialized strategies to switch data packets to their destination explicitly. It caches the information generated by layer 3 routing engine even before the switch encounters any of the data flow. The CEF cache routing information in one table, our FIB, and then caches layer 2 next hop addresses and frame headers and the header rewrite information of all the FIB entries in another table called our Adjacency Tables. So our forwarding engine for our layer 3 is consistent for our FIB and Adjacency Tables, and that way the packets will be processed here with those. Alright, let's get into our fib a little bit better. What is our forwarding information base? It is derived from IP route tables. It is arranged for maximum lookup throughput. IP destination prefixes are stored in our TCAM, from the most specific to the least specific. Fibs look up based on layer 3 destination address prefixes. Match structures to our CEF entries with our TCAM tables. When the TCAM is full, wildcard entries redirect frames of the layer 3 engine. Updates after each network change, but only once. Lastly, contains all known routes. Contains all next hop addresses associated with all destination addresses. So let's talk about our adjacency tables. Okay, our adjacency tables are again derived from our ARP tables and contain layer 2 header rewrites of the MAC address information for each of the next hop containers. Maintaining layer 2 next hop addresses and link layer headers, all of it is stored in our fib entries. It populated as adjacencies as they are discovered, and each time the adjacency entry is created, such as via an ARP request, a layer 2 header from that adjacency node is pre-computed and stored in the adjacency table. Adjacencies, or rewrite information, and statistics are maintained by specialized components. CEF maintains a one-to-one CEF to adjacencies mappings for accurate statistical tracking. So the different types of adjacencies are punt adjacencies, are drop or discarded adjacencies, or are null adjacencies. The important one here is our punt adjacency is used for packets that require specialized handling by layer 3 engines or features that are not yet supported by hardware switching. Some of our packet type forcing software processes, that's going to be use of IP header options, maybe expiring IP TTLs, forwarding to a tunnel interface, arrive with non-supported encapsulation, routed interfaces with non-supported encapsulation, exceeding the maximum MTU size, or even NAT. Not all packets can be processed in the hardware. When traffic cannot be processed in the hardware, it must be received software processing by the layer 3 engine. This traffic does not receive the benefit of expedient hardware-based forwarding. What about ARP throttling? An important feature of CEF-based catalyst switches is ARP throttling. Make note that ARP tables build the CEF adjacency tables. When a router is directly connected to a segment shared by multiple hosts, such as Ethernet interfaces, the router maintains an additional prefix for all the subnets. The subnet prefixes point to a glean adjacency. When a routing receives packets that need to be forwarded for a specific host, the adjacency table is gleaned from the specific prefixes. If the prefix doesn't exist, the subnet prefix is consulted, and then the green adjacency indicates the addresses within the range, and that the fact that they should be forwarded out a layer 3 engine for ARP processing. ARP throttling is a way to help throttle our ARP requests so they're not using as many resources. Moving past that is our CEF operations. You guys can go through the CEF operations, but essentially the host will send a packet from A to B. The switch performs CEF lookup based off the destination address. The packet hits the CEF FIB entry, shows that it's connected to VLAN 20, and then the engine is using a glean adjacency. The hardware switching CEF table cannot forward this packet because it does not have the rewrite information. So step 3, the layer 3 engine installs an ARP throttle adjacency in the switch for host B's IP address. Step 4, the layer 3 engine sends an ARP request to host B on VLAN 20. Step 5, the VLAN B sends an ARP response. The layer 3 engine installs and resolves the adjacency in the local adjacency table. Step 7, the switch receives another packet from host B. Step 8, the switch performs the layer 3 lookup, finds a CEF entry for host B, and you're good to go. Alright, moving on, CEF Load Sharing. Up to 6 adjacencies for a single fib entry for a Catalyst 6500 series switch exists. For load sharing per destination, CEF selects a particular adjacency based on the hash of the following packet characteristics. Remember, the default varies with Catalyst switch families. But the packet characteristics are our source IP address, our destination IP address, and or the source and destination IP layer 4 ports. Because CEF by default will always select the same path for a given host pair, CEF polarizes the traffic. CEF polarization decreases as the number of hosts pairs increase. In a smaller network, CEF tunes or tuning may be required. Configuring a CEF. The Cisco Catalyst switches use CEF-based MLS architecture. MLS is multi-layer switching. For Catalyst switches that support CEF-based MLS, CEF and per destination load balancing. This is all nice fun switching terminology. Yay. The network engineer should not disable CEF on Catalyst switches for any reason except under the supervision of a Cisco TAC engineer. Describing or disabling CEF on a Cisco Catalyst switch yields low switch performance. Verifying. You can verify CEF information by doing show interface and the interface, show IP CEF, that verifies the fib. If you want to verify detailed information about a particular VLAN interface, you can always do show IP CEF, the type or the port, the VLAN interface, and detail. If you want to look at the adjacencies, that would be show adjacencies, the type or port, pipe in port channel, or details or internal or summary. Here we have a quick show interface port channel 9. This is an Ether channel VLAN 9, and it gives you all of the switching information. Displaying our Cisco Express forwarded fib on a multi-layer switch, you can literally just do a show IP CEF, and you will get the CEF fib information. The layer 3 engine CEF table determines the hardware switching CEF table. As such, in troubleshooting any CEF issues, the first step is to view the software CEF table, so you can then use the show IP CEF command to display information about entries in the fib. Displaying CEF adjacency table information, you can do show IP CEF VLAN 10 in detail, and you will get the appropriate VLAN information. Verification, again pretty straightforward. Show adjacencies, double check the table. Troubleshooting CEF, the general 5 steps: verify the IP, verify the next hop, verify the IP and the fib table, verify the CEF table, and when all other troubleshooting steps have been exhausted and the CEF-based MLS switches is still experiencing Unicast routing issues, verify the population of the fib and adjacency tables in the TCAM under the supervision from a TAC engineer. That's actually it for our Chapter 2. I want to thank you guys, and I hope you guys have a great day.